College Algebra, Chapter 5, Section 4, Logarithmic Functions. Okay, our exponential function a to the x is 1 to 1, so it has an inverse, and that inverse is called the logarithm. And as you look here, you see the progression. First you switch x and y, and then you solve for y. And when we do that, it looks like this. Y equals log base a of x. A was the base in the original problem, and we still call it the base. Notice where it is now. The y, what we're actually getting as our answer here is the power. In the original equation, we were raising a to the x, we were raising a to a power and getting y. Now we are asking ourselves, what power do we need to raise a to in order to get x? The logarithmic function with base a and the exponential function with base a are inverses, so when you compose them, in both cases you get x as the result. Remember that the graph of an inverse function is a reflection of the original function about the line y equals x. So you see here we have an example both hand-drawn and on the calculator. We have y equals 2 to the x, which is the red graph. We have the dashed line representing the line y equals x, and then the blue graph, which is y equals log base 2 of x, the inverse. And you can see how they're reflections. It doesn't look quite the same on the calculator. Remember, though, there's a little bit of a stretch going on there. You notice that the hash marks for the x-axis are farther apart than for the y, and that does distort the image just a little bit. So the figure above is the typical shape for graphs where a is greater than 1. This includes base e and base 10 graphs. So when you have the base is greater than 1, it's going to look pretty much like the blue curve here. And these are the shapes when your base is between 0 and 1, when it's a fraction between 0 and 1. And again, it's a reflection of the inverse function across the line y equals x. Okay, here we have the function capsule for log base a of x, where a is greater than 1. The domain is 0 to infinity. The range is negative infinity to infinity. It's increasing and continuous over the entire domain. You'll notice that the y-axis is an asymptote, and the graph goes through the points 1 over a, negative 1, 1, 0, and a1. This is the function capsule for when our base is between 0 and 1. Our domain is the same, and our range is the same. What has changed is it is now decreasing. It is still continuous, but it is now decreasing. The y-axis is still a vertical asymptote. It goes through the points a1, 1, 0, and 1 over a, negative 1. And we're going to find the domain of each function. All right, why don't you pause the recording and see if you can do this, and then resume to check your answer. Okay, for part A, the argument of the logarithm must be positive. In other words, the x minus 1 has to be positive or greater than 0, because you can't raise 2 to a number and end up with a negative. So x minus 1 has to be greater than 0, or x is greater than 1. So the domain is from 1 to infinity. Now, if you didn't quite get that the first time, try part B and see if you can get it this time. Pause the recording to do that and resume to check your answer. Okay, for part B, we have to get a little bit more complicated. We need x squared minus 4 to be, again, greater than 0, and we're going to use a sign chart to do that. And the book does it slightly differently than we did in class. Either way is fine. But when you do the sign chart, you factor it first. You see where each factor is positive or negative. Again, we want it to be greater than 0, and it's greater than 0 when it's less than when x is less than negative 2, or when x is greater than 2. So the domain for this function is negative infinity to negative 2 combined with 2 to infinity. Okay, now we're going to give the domain, range, asymptote, and x-intercept. Okay, pause the recording, see if you can do this, think about what we just did, and then resume to check your answer. Okay, so for A, again, the argument shifts the graph 1 unit to the right. So our vertical asymptote is now going to be x equals 1 instead of the y-axis, which is x equals 0. Our x-intercept is going to be 2, 0, and the domain is from 1 to infinity. The range isn't going to change. It's negative infinity to infinity. For part B, we're taking the log base 3 of x and subtracting 1. So it's going to shift the whole thing down 1 unit. The vertical asymptote is not going to change. The x-intercept is going to change slightly. It's going to be 3, 0. The domain is 0 to infinity, and the range is negative infinity to positive infinity. Now we're going to show analytically that the graph of f of x equals the natural log of x squared minus 4 is symmetric with respect to the y-axis. Being symmetric with respect to the y-axis means that it can be reflected over the y-axis. So what you're going to do is you're going to show that when you put a positive value in for x, say 3, whatever y you get, you're going to get the same y when you put in negative 3. Okay, so what you're going to do is you're going to replace the x with negative x and show that you end up with the same result. Okay, pause the recording, give it a try, and resume to check your answer. Okay, so here we're putting in negative x in place of x, and when you square a negative, it becomes positive, which means we really haven't changed anything. So it is symmetric with respect to the y-axis. Now we're going to find the inverse function. Okay, we've got an exponential here. Remember, we're talking about logarithms. Logarithms are the inverses of exponential functions. All right, see if you can figure this out. Pause the recording, give it a try, and resume to check your answer. Okay, the first thing we do is we're going to swap out the x and y values. So we have x equals negative 2 to the y plus 3. Then we're going to get the 2 to the y by itself. So in order to do that, what they did here was they added 2 to the y to both sides and then subtracted x. There's different ways you can accomplish this, but you should end up with 2 to the y equals negative x plus 3. And now we're going to rewrite it as a logarithm. The base becomes the base of the log, so we have log base 2. What's after the equal sign becomes the argument, and then y is on the other side, the equal side. So we have y equals log base 2 of negative x plus 3. And then we replace the letter y with the f inverse of x. Now we're going to use a logarithm in an application problem. So we have a formula here for the concentration, the intervals of time in hours when a drug should be administered, because the effectiveness decreases over time. So T equals 1 over K times the natural log of C sub 2 over C sub 1. K is a constant determined by the drug in question. C sub 2 is the concentration at which the drug is harmful, and C sub 1 is the concentration below which it is ineffective. So if you worked this out and you got that T is 4, that would mean the drug should be administered every 4 hours. Okay, so for a certain drug, they're giving you the information here. K is 1/3, C is 5, C sub 2 is 5, C sub 1 is 2. How often should it be administered? Find T. Pause the recording, give it a try, and resume to check your answer. Okay, this is really just a matter of putting the numbers in place and then putting it in your calculator. So hopefully you didn't have any problems with it. You should get 2.75. This is going to be just some extra practice for you. So as you go through these, pause the recording, try the problems, resume to check your answer, and continue this way through the rest of the recording.